Welcome back to Maths with Mrs. J. We've started talking about graphs of trig functions. And what I would refer to as your basic garden variety graphs are your very basic y equals sine of x, your very basic y equals cos of x, and your very basic y equals tan of x graphs. 1 period's worth of your sine of x, starting at the origin, looks like this. 1 period's worth of your cos of x starts up at 0, 1 and looks like that. It, in effect, is your same as your y equals sine of x, but it's been translated horizontally. Your y equals tan of x looks like this, and you have vertical asymptotes everywhere that cos of x would be 0, so everywhere on your vertical axis. For your y equals sine of x, just your garden variety one, the amplitude is 1 and the period is 2 pi. Same for cos of x, same period, 2 pi, same amplitude. For tan, we said that it didn't really make sense to talk about an amplitude because, of course, it's heading up towards infinity and down to negative infinity. However, the period for tan is pi. And we talked about the fact that in our unit circle, tan is exactly the same in the first and third quadrants and in the second and fourth quadrants. So every pi, it repeats itself and you have those vertical asymptotes. Now, thinking about basic changes that we can make to the format and what's happened in the past when we've talked about quadratic functions, we've talked about all sorts of different functions and how these little changes affect the graph, we should be able to fairly easily adapt these pictures to reflect those differences. Whether you have a plus or minus out the front basically determines whether you're going to have the normal garden variety or the upside down version of it. Your A is going to affect your amplitude. So if you had a -3 in front of your sine of something, you know it's going to go up to 3 and down to -3, and it's going to be upside down. Now, B affects the period. What happens is it makes it repeat itself more often if B is a bigger number. So the period becomes 2 pi divided by B. So if B was 2, it would then repeat itself every pi. So you get 2 repetitions when you would normally only get 1. If B was 3, you're going to get 3 repetitions when you would normally get 1. C is our horizontal shift. Because it's a -c, it's to the right if you have just a -c. It's to the left if you had a +c. Remember, +c is the same as -c. We have seen things like this before with other graphs, whether it be quadratic or whatever. Shifting to the right or left often occurs when you have an x minus something. Your vertical shift, again, that's a very common change that happens to a graph. If you just have the normal function and then you add something to it, you're just shifting the whole lot up by that amount. Of course, if D is a negative number, you're shifting the whole lot down. Okay, let's have a look at my way of drawing these graphs. Now, it is slightly unusual, but bear with me. I actually do it in a way that's quite different from the way that's taught at school. This is Mrs. J's method, all right? Rather than starting with my axes and then trying to draw my function, I start with my function and pop in the axes, and I'll show you how it works in just a tick. By the way, you can buy little like math aid things where you can trace along to get a really nice shape. You can get them anywhere. I don't get any like kickback money from them or anything like that, but you can buy them at you know, stationery shops, online, that sort of thing. If you really want to, you can get those that are applicable in exam situations. You just get the ones without the formulae on them. All right, this is how I do it. So first thing I do is I look at the function and I work out what is the amplitude, the period, the horizontal shift and the vertical shift, according to what's happened with our function. What changes have occurred with our function and how do we work around that? So let's do that for this example here. It's going to be an upside down one. So let's just make note of that. Okay. What's our amplitude going to be? Our amplitude is going to be 3. The period is going to be the normal period of a sine curve, but divided by this number. We're going to get that number of repetitions every 2 pi. So the period for this particular function is going to be pi. The horizontal shift, we've got a minus pi on 4. So we've shifted pi on 4 to the right. And because of this plus 4, the whole thing has been shifted 4 up. So that's my first step. I work out the various changes to the formula and what difference they've made. Then what I do is I sketch 1 period's worth of the garden variety function, upside down if necessary. You know, in this case, it will be necessary to do it upside down. So I'm going to use my little stencil to trace 1 period's worth of a garden variety sine curve, but upside down. So I'm going to do that here. I can thankfully pick it up and move it if I need to. So here we go. I'm going to just select that and move it a smidge. Okay. Now what we're going to do is we are going to have a look at our next step in the procedure. We're going to use our amplitude and our vertical shift to work out the y values at crucial points. What do I mean by crucial points? Well, crucial points means the y values at sort of this point, at the top point, and at the bottom point. So normally, if you have an amplitude of 3, right, this would be at a y value of 0, okay? Normally, if you have an amplitude of 3, this would be at a y value of -3, and this would be at a y value of 3. However, we have moved the whole thing up by 4. So this is now a y value of 7. This is going to be a y value of 4. And this is going to be a y value of +1. So we've got 7 is the y value there, 4 there, and 1 there. So divide that into 3, and we go 1 lot below that, and do a horizontal line. That will be approximately where your x-axis will be. Your x-axis occurs when y is 0. So let's do that. Get something like that. Now this is not meant to be perfectly accurate. It's not meant to be something that you're going to be reading values off or anything like that. It's just to give a sketch of the basic shape and what's happening to it. All right, so bear that in mind. So that's our x-axis there. Now we're going to use our horizontal shift and the period to work out the x values again at the crucial points. Now by crucial points, I mean at the start and the end and halfway in between, that sort of thing. So the x value here would normally be at 0, of course, but because we've had a horizontal shift of pi on 4, that's now pi on 4. The period is pi. So from pi on 4 to here, we're going to add pi. So that's 5 pi on 4. Halfway is here. So that's going to be at 3 pi on 4. This will be halfway between pi on 4 and 3 pi on 4, which is 2 pi on 4, which is pi on 2. And this will be halfway between 3 pi on 4 and 5 pi on 4, which is pi. So let's actually write these in the proper spot. Let me just get rid of those. Get rid of that down there. And okay, so this is at pi on 4, 3 pi on 4, 4 pi on 4, 5 pi on 4. So each of these distances is pi on 4, and we need to pop our y-axis at 0. So we need to go pi on 4 to the left. So we're going to pop our y-axis there. Something like this. Let me just pick it up and shift it a smidge. Something like that. And then we can actually pop in our values for there. So this was at 1, 2, 3, 4, 5, 6, 7. I would actually use a ruler normally. So let me just go through that process again. We look at the function, we work out what changes have been made to the amplitude, the period, if there's been a horizontal and vertical shift. Draw 1 period's worth of the function using a stencil or whatever if you like. In this case, we needed to do it upside down because we had a negative. Then you're going to use your amplitude and your vertical shift to work out the y values at various important points. So sort of halfway, obviously, at the bottom and at the top. And you're going to place your x-axis where y is 0. Then you're going to use your horizontal shift and the period to work out these x values, and then obviously put your y-axis where x is 0. Then all you really need to do from there is just obviously write the function on it, and I would just continue that function a little bit in both directions just to sort of show what's going on. So it's going to come up to here. This isn't going to be perfect, but it's okay. It'll give us the basic shape. We're going to have that sort of thing happening. And there you have it.